Thank you so much.
Thank you, Roberto, for the invitation. My name is Graziella Devoli. I'm a geologist mainly and researcher at the Norwegian Water Resource and Energy Directorate in Oslo, Norway. I'm working mainly with rainfall-induced landslide and specifically with the organization of the operational landslide early warning system. And as you know, the operational landslide early warning system are very complex. They need a lot of activities, and we need to jump from pure research to more routinary work. And in particular, in this presentation, I want to focus on the quality control of historical landslide. Already Dr. Marchesini mentioned how is important the quality control in order to calibrate the model. And in particular, we are going back to control the historical landslide data because the main purpose for us was essentially to create a landslide index based on landslide threshold analysis in order to operate the Norwegian landslide early warning system. But before to introduce about the quality control, I want to mention briefly what is the Norwegian landslide forecasting early warning service. We are part of a different type of let's say five main early warning system at NVE. We have three of them that are national and regional, and so the one that I will present today is debris flow, debris slide, and slush flow, which was start to be operational in October 2013. And we work together in synergy with the flood, which is the longest early warning system. Also we, during the winter, we also cooperate with the snow avalanche service. There are also two other landslide, not landslide, but two other local early warning system for unstable rock slopes, so for large rock avalanche, and also for ice condition on a lake and rivers. Of course, we have to do a lot of activity in order to working every day the landslide early warning system. So first, we start with to receive input data every morning, which are essentially weather and hydrological forecast, and also real-time observation, mainly for water discharge, but also snow condition or rainfall condition. These input data are sent in our models. We have hydrological models, snow model, and landslide model. And we create from this model grid-based maps, thematic maps that are possible to visualize in a decision tool that is available online. And from the combination of this input data and model output, also expert knowledge and the daily briefing with the meteorologist on duty, we do the daily hazard assessment, and we decide if, of course, we should send a warning or not. And the warning are later published and disseminated through specific web page. And the specific tools, dissemination tools in case of orange or red warning. And when we send this warning, we hope that the emergency management they take action. Of course, we have a regional office at MVE, which are distributed in different parts of the country, that they try to assist every day the municipality, and during the emergency they activate it in order to help them. And finally, we have the evaluation that can be done weekly or monthly, months after a specific event. And this is done by looking at which recorded event, what has occurred, and the impact. In terms of landslide, actually our forecasting and warning service, it's focusing on, let's say, rainfall and snow melt induced slope failure. So we include also, we include, of course, in this category, debris avalanche, debris flow, debris slide, and slash flow. Today, I will not talk specifically slash flow, just I will mention briefly. So the quality control that I will talk about is focused mainly on these three types. Also, I want to introduce how the landslide threshold analysis has been performed, and the landslide index that we are using at the moment. So the first, or let's say the landslide threshold that we are using now, and the landslide index that we are using now, was done in 2009-2010 using a data set of about 250 landslide events that were extracted from the national database. These events, as you can see in the map, correspond to events that have been chosen randomly, mainly because they were well documented at that time when the work was done. In particular, we had landslide event that occurred in autumn 2005 in two periods, 14 of September and 14 of November, which were essentially rainfall rest of extratropical cyclone that arrived far up to north to Norway. Also, we had 15 events that these in green that are associated to snow melt, quite intense and long-term snow melt episode in spring 2008. And also we have this data set that occurred in autumn 2000, which were associated to high soil saturation due to prolonged rainfall from a long period between September and December 2000. So what we did, we didn't use a meteorological station as normally is done when we do rainfall threshold analysis, but we look at a grid cell close by or where the landslide was located. We had grid data for a different type of hydrological parameter obtained from the distributed version of the HPV model. And as you can see, we had different type of grid map, for example, representing the rainfall, the daily rainfall, or the daily rain and snow melt the daily soil saturation, degree of soil saturation, or the daily groundwater level. So what we did was, okay, we look at the cell, and so we say, okay, in this, the value of this parameter was a defined value for the day when there was a landslide, but also we collect for the same cell the value for 14 days before and 14 days after, when the landslide was not there. And so, but also this selection was done manually. So here you can see, maybe it's not easy to see, there are this green dot, which are the landslide, which are actually landslide related to this spring 2008. And here we see four different landslide. These are the grid cell code that we have been chosen for to create this landslide value, this hydrometeorological value. And as you can see, this was done manually, and we look essentially at the closest grid cell that has the highest value, or where we was supposed. Or we choose let's say the cell that we suppose was close to the initiation area of the landslide. So at the end, we plot this, so we combine a different type of hydrometeorological parameter, and we found that the best combination at that time was the water supply, which is in the vertical line, and the degree of soil saturation. Both of them were relative value to a period from 1990 to 2008. And here we plot, the blue are the value of day without landslide, and the colored square point are those for the different data set. Of course, this landslide threshold take inspiration from previous landslide threshold that were available for Norway, which was Sandersen et al. From 1996, but it was improved based on soil saturation from hydrological model. From this threshold, so this is quite strange compared to other threshold that we see in literature. But from this threshold, we obtain a grid version of the landslide index. And this is the reason, since we are working with grid, we decide to have this kind of step line instead of continuous line. Between 2011 and 2017, we did some improvement on the landslide index, and we decided that, of course, we have, if we want to introduce more landslide, we need to do a selection and control, and of course we have to focus only on landslide triggered by rainfall or snow melt. We do not need landslide due to other type of triggering mechanism. We need also landslide that have a good accuracy in terms of date and time, and also we want to avoid the double registration. The landslide threshold that we use now is a combination actually of three thresholds. So we have the landslide threshold for the entire Norway, the one that we see, which is for this area, and we have also one specific for these two other areas here in southern and Norway and southern eastern Norway, and this was done because we have too many false alarm. So during this improvement of the threshold, we we discovered the poor quality of the landslide event recorded in the database. There was a lot of uncertainty related about the landslide type, date and time and location. Also, the landslide were recorded as points, and we had to guess, let's say, the starting area in order to collect the hydrometeorological parameter. And also the control, the data that we have control in this two period, we could not send again into the database. So this indicated that we have to create a new control each time we want to do new analysis, and this was of course time consuming. Just to mention some of the problem, we see that the Norwegian terms URAS or URSKRED is, we try to use these terms specifically for debris avalanche, and in some cases used also for debris flow. And you know that this type of landslide are rainfall and snow melt induced. However, we see that in the database, these terms, it's also used to identify, to register clay slide, where the soil saturation is more relevant, or sometimes is just an anthropogenic factor that are more relevant. So we want to separate this type of registration in terms of landslide type. Also, another common problem is debris flow. Actually, we know that the debris flow can have different way, or they look like differently because they have different phases. And we use actually Norwegian terms. We have only one terms, which is flomskred, which is used for debris flow, the water stream flow. And we understood quite early that they are represented in the database, and this was essentially because many of them, especially when you have a debris flow with a lot of big blocks, is reported as a rockfall and not as a debris flow. Also, we found out that in the database there are some events recorded with the same name, but in reality, when we look at them, they are just water with some gravel, and so maybe this is not a classical debris flow, so maybe should not be reported in the database. So the question was, can we perform the control directly into the database in order to avoid new control each time we want to do new landslide threshold analysis? So how to move? Okay, so in this last part, we look at the quality control and which procedure we have been used, and the lesson learned from that. So first, the quality control was done directly into the landslide database. I have to mention that the landslide database is actually a national database of mass movement, because it includes also snow avalanche and landslide, but also submarine landslide. Drift by the Geological Survey of Norway, and later was transferred at MVE, and you can have the link. You can look at the database in this link, and also you can download the data directly from this other link. In the database, there are about more than 90,000 recorded landslide and snow avalanche in the category of landslide, snow avalanche, slash flow, ice fall, and submarine landslide. And in the landslide, we have landslide in rock and landslide in soil. In particular, in the category of, we are interested in the category of landslide in soil, where there are circa 12,000 of recorded. But here we include also debris avalanche, clay slide, and quick clay slide, so all type of landslide soil. In 2014, when the database was transferred at MVE, we create a super user account and tool to make possible the direct control into the database. And we proposed the first quality level, which were essentially 3. In order to be a good quality landslide record, we need that at that time we proposed that the date should be plus minus 1 day. The position should be with an accuracy of plus or minus 50 meters. And if it's possible, we should have the landslide polygon, and the landslide type should be correct. Later on, we have introduce more 4 actually quality level, and this quality level is essentially are essentially focusing on the location, on date and time, landslide type, duplicate, and documentation. Here I will not I will focus only on the criteria that we choose for the debris avalanche and debris flow. So a landslide of quality A should have a polygon represented at the source and runout area of plus or minus 10 meters. Of accuracy, and the date should be plus or minus 6 hours. The landslide type should be well defined based on the information available in the documentation. And usually this type of landslide are well documented. We have many sources and pictures or aerial photo. A quality B is has a source area and a runout of plus minus 50 meters of accuracy. We can have a polygon that usually represents the runout area, but here we do some exception for the slash flow and debris flow, where we accepted in this category also event where the source area has a accuracy of plus minus 500 meters, and this is because many times we do not exactly where the landslide start, especially when debris flow start as a runoff or erosion in the gully. Here we accept about plus minus 1 day and of date, and these are partially documented. Usually we have a picture representing part of the landslide, so we could not see the entire landslide. And for C and D, of course, we have a landslide point with more inaccurate in terms of location. Can be sometime some documentation, but we cannot have more information. And D is quite uncertain, and we know that, let's say that there was a landslide, but we cannot say much more because we lack of documentation. As I mentioned, at the moment we have registered 12,000 landslide soil and more than 1,000 slash flow. But the number that can be possibly relevant for threshold analysis are essentially only the event that have occurred after 1957, because from this date we have grid data for hydrometeorological parameter. And so we have when we look at the event that we have controlled after this period, we can see that more or less 1,000 slash flow, and 6,000, more than 6,000 could be potentially used for threshold analysis. In particular, if we focus on debris flow and debris avalanche and debris slide, we have at the moment control circa 2,000 of events, and here you can see in this map those that got a quality level A, the best, and the quality level B. The majority has a quality level B, as you can see. If we look in terms for these three type of landslide, if we can see the different level, we still see that there are many recorded as a register and not control. So we could, many of these could eventually reach a category A or B. So the main contribution of the quality control process in terms of for the purpose of the landslide early warning system, it was extremely important, because we now have an improved data set that we can use for landslide threshold analysis and landslide index, and also for the evaluation of the performance. Also, this quality control process has contributed to the improve the description and the mapping of debris flow and debris avalanche. As I mentioned, 2,000 or around 2,000 can be used for future landslide threshold analysis. Also, we have a polygon of starting area or initiation point that we could use in order to automatically select the grid cell and collect the hydrometeorological value. And also for slash flow, we have definitely more improved data. And so we could create a similar slash flow index that at the moment is not available. So some of the lessons learned: we can improve the quality of historical landslide event. Yes, but this depends a lot from landslide type. Some landslide, like for example, quick landslide, are better documented, and so it's easy that for the majority of them has a better quality. For the debris flow and debris avalanche, we struggling to get better information. And we see that we cannot always improve the quality, especially for event before 2000, because we do not have a lot of aerial photo available or technical report. We are interested, as I mentioned, to collect to control only the landslide that occur after 1957. So we are not looking at to control everything. We think that the best is to have a few data, but with high quality, instead of have many events with a poor quality. Also, we realized that the control should be done for landslide that has been triggered by the same hydrometeorological condition, and not using, for example, administrative boundary for region that otherwise it's too complicated. So the organization of the control was done start almost immediately. in 2011, when it was officially decided to create an operational landslide forecasting service. The work was done by us, so me together with 2-3 other people from MVE, but in the almost from the beginning we use a collaboration of bachelor and master student, and in totally we have been involved between 25 and 30 people in the last 10 years. We use mainly students from the University of Oslo, but other students from other university have been involved. We had a kind of summer job agreement, so they have been work during summer from June to August, more or less. And initially this work was done with a research project, so finance using internal funds for research project. But after we, from 2022, we have an assigned budget. The control also start only with rainfall-induced landslide because of the interest of the landslide threshold. But in recent year, we have extended the control to other type like slush flow, quick clay slide, or rock avalanche. And since 2018, this it's more systematic. We started the control from the recent event because they are better described, and we move backwards. We have used different type of instrumentation, and yeah, we also use the student involved in the preparation of written documents. Of course, this has been very useful not only for landslide early warning purpose, but also for hazard mapping, for the calibration, for example, of landslide model that simulate the using in, for example, for susceptibility and hazard map. We improved also the registration. We propose improvement in the registration tool. We learn a lot from this experience, but also it was a big learning moment also for the students. And we have written a method for control, and we prepare written routines and rule. And here I will show at the end some of the reports that we have written about the quality control. And also there is a web page where we have information. The same information is also available in our web page. We have created also some extra learning information, like, for example, how the difficulty that we have in drawing some polygons, for example, and what could be an example of the different quality level. Just to finish, we had, for example, the most recent control of landslide was done after the storm Hans that occurred in August 2023, which was one of the most expensive natural disaster in modern time in Norway. Under this storm, there were recorded more than 700 landslides in soil between the 7th of August and 10th of August. Here we can see the rainfall, the forecasting rainfall for the 7th of August. And here you can see the landslide index that show a lot of high danger level for both for the 7th and the 8th of August. And we send a red warning for 3 days, and after we yellow for the rest of the week. And here you can see the location of all the landslides that have been controlled. We had a student that worked once a week for a period of 6 months, and he put together the data set that have been obtained by university and the private consultant that have been working in the affected municipality. And here's some of the example of the landslide that occur during this event. Yeah, so thank you for your attention, and please ask question if you, or contact me if you need more information.